Hello. In this video, we're going to be taking a look at what we call function notation, which is essentially a fancy way to say the way that we choose to represent a function in terms of its equation particularly. So to start off, let's consider this. This is the equation of a line, and in particular, this line has a slope of 2 and a y-intercept of 3. Those are written in those normal spots where you have like y equals mx plus b, where those variables m stands for slope, b stands for y-intercept, and you can change those to essentially pick which line you want. In particular, in this equation, we also have the variables x and the variable y. Now, these two variables are always going to be found in your equation for a line, assuming that you choose to plot your line on, pardon the squiggly lines here, a coordinate axis, where you have the x-axis here and the y-axis here. Now, looking at this equation, we say that y is a function of x, and this is assuming you're dealing with an equation that actually has it be the case that every input can have exactly one output. For example, here, if I were to draw this line, let's imagine we have 1, 2, 3, that's my y-intercept, and let's say I can go up 2 more, over 1, I put a point here, and I could then draw a straight line, hopefully, through those 2 points. That looks pretty good. That could be my line. And notice in particular, as you consider every, I'm going to choose like, let's go light green. If I choose any input here, if I trace up to where it hits my line, there is only one output, only one y value associated with that input. And so we call it a function of x, in that every x, if you pick an x, you can find exactly one spot on your curve for which there is a output or a y value. So we say y is a function of x. If we know what x is, we can uniquely determine what the y value must be. Here it looks like it's probably going to be like 8 or something like that. If we try that out, if this is like, I guess this is 2, then we have, wow, I was very close but very wrong. You'd have 2 times 2 plus 3, which is 4, plus 3, which in this case would be 7. So your output there would be 7. If you know what x is, you can then determine what y must be. Y is a function of x. Now, that's all good. However, there's another way that we could choose to represent this. Now, y, which is a fancy word for the output. There's no reason that we necessarily choose y other than the fact that, like on the coordinate plane, y is often used as that variable representing that axis. And because y is essentially arbitrary in our choice of it, we can actually use something else. And what I'm going to choose to use is something called function notation, which looks like the following. So I'm going to write the same equation as well. Now, we said that y is a function of x. So what we could do is just essentially write that. So we could say what we call f of x, in quotes. That's how you pronounce this guy right here, what I was initially drawing, this f of x, f parentheses x. And we say it's a function of x. We say that this whole expression is a function of x. And why do we say that? Well, if we know what x is, we can determine what the function will output. In this case, like up here, we had if f is 2, or if our x is 2, our function takes us to the point, in this case, I think it was going to be 7 when I did it out. Now, why this notation? Well, if you notice here, we have x written in parentheses right here. And we also have the f there to represent that, like, this is a function we're dealing with, but x, importantly, is right here. Notice it's meant to be, or maybe I'll tell you, it's meant to be the same x that's here. If it was a different thing, then we would just like write y instead. If it did not represent the same thing, in math, if you ever see the same variable in two different places, assuming you're in the same context of a problem, or in the context of the same problem, it's going to mean the same thing. That's why we use variables of the same sort to represent the same idea. In this case, the input. And so we say your function of x being your input, is equal to Well, a function of x, where you take the input, you do some stuff to it. Here you multiply it by 2, then you add 3, and you get some output. And oftentimes we write f of x to represent, or like f of x is the output. For instance, whatever this is equal to is the output. And we say, like, instead of y, we write f of x. So y and f of x both stand for the same thing. The entire expression f of x means the output in terms of like how we can essentially read it or interpret it. Now let's go ahead and see some concrete examples. So earlier we plugged in 2. Function notation, remember we have the input written in parentheses. Imagine I were to write, I'm going to use pink here, f of 2, and then we could write is equal to, well, 2 times, I'm going to make that plus 3, 2 times 2, and then of course this would equal, I'm just going to go ahead and write in white, equals 4 plus 3 equals 7, and we still have, I'm just going to copy paste it, f of 2 and f of 2. Now the benefit of function notation is at the very end here, you see we have f of 2 is equal to 7. Well, what this does for us is it helps us essentially keep track of what we're doing. F, and importantly f of something, tells us that we're dealing with the initial function, f of x. The name f of x refers back to this, and typically when we have a problem, if we want to define a second equation, we'd write like g of x equals 3x minus 2 or something like that. If you were to have a second equation, you would typically just change the name of it. So you can refer back to, hey, this f, it uniquely means this equation that I defined it to mean. Compare that to, for instance, if I were to have another equation up here, I said y is equal to 3x minus 2. If I wrote at the very end that y equals 7, well, which one am I talking about? Am I talking about the first equation? Well, obviously, that's what we got here. Or am I talking about this first one? If you were to name your function, such like here where we have f of something, you can refer back to, hey, that's exactly what we meant here. Now, of course, you could technically change the variable to be like y, but then, or sorry, w, but that would also be kind of weird because then you'd have to make a separate coordinate system and it would be just a whole mess. Now, another benefit is that notice here we're plugging in the input. At the very end, you just have 7. Well, just looking at the right side of the equation, you can't tell what you plugged in to your equation. I mean, if you look backwards, eventually you see, oh, we plugged in 2, or you see the x. However, on the left-hand side, we kind of keep track and, hey, this is what's happening as we go along. Each step is what happens when you plug in 2. 2 into, plug 2 in to the function f. You keep track that if you plug in 2 as your input to the function f, you will get an output of 7. Notice again, this whole thing is the output of this equation when you plug in 2. Compare that up here. I look at y equals 7. I don't know what function it is in particular that I'm plugging into, unless I only have one referenced. And then I also don't know what I plugged in. I just see that it's equal to 7. So this notation, function notation, allows us to keep better track of what you're doing. Now let's go ahead and see another example of what we can plug in. Let's say, imagine we have f of, I'm going to make it a bigger equation, or a more complicated equation. Let's say it's like x squared minus 2x plus 3, or something like that. Well, imagine now that I took this and I plugged in, let's say 3. I'll use different colors to make it fancy as well. Well, again, x stood for your input, and so wherever you see an x, this is a function of x, you can plug in, I'm going to use parentheses there, minus 2. Wherever you see x, you'll plug in the input, because x is the input, and here you're storing that the input is, in this case, 3. Well, this is now equal to, well, we'll have, I'm going to copy that down a few times. We're going to simplify maybe 2 or 3 times. So I'm going to copy twice. If I need to add more, I will. This is equal to, well, I'm going to use, let's use yellow, why not? It's equal to 3 squared is 9, minus, that's a minus sign right there, 2 times 3, which is 6, and then we add 3. And then we can do 9 minus 6 is 3. And then you add 3 to that, you should get the f of 3 is equal to 6. And here, of course, we can look at this and say, okay, our function f, which we can refer back to very quickly, which is this expression there. If you plug in 3, you get 6. So f of 3, the output is 6. Nice. All right, now, what's also cool about function notation is that it allows us a nice way to interpret what we call transformations. Now, I'll talk more about specific transformations and what those transformations mean in another video or another set of videos. However, right now I'm going to talk about notation and why this is so nice. So imagine your function again. Let's just use the first example. So we have 2x plus 3. What if I want to modify this equation? And keep track of the fact that I am modifying this equation. Well, what are some modifications that I could do? Well, maybe I think this is too small, and for whatever that means, it just maybe I want to make it bigger, in the sense that I want the outputs to be twice as large as they are. Well, I could take my function and just multiply it by 2. So 2 times f of x, taking all the outputs of your equation and multiplying them by 2. That's one thing you could do. Well, in this case, you'd have 2 times 2x plus 3. And so the equation function 2 times the original function is equal to, in this case, 4x plus 6 if you go ahead and distribute that 2 into the parentheses. And so we can store that twice your function is equal to 4x plus 6. It's a nice way to store that. If you wanted to modify I'll just keep the chain going here. Maybe you want to also, so you have 2 times f of x, and you want to additionally, maybe you want to raise it up by 5 for whatever reason. You want to make it each input then 5 larger. So you make each input initially double, or output double what it initially was with this multiplying by 2 business, and then you can add 5 to it. Well, here, you can take what you had before, and you could say, you can either go 2 times 2x plus 3, in this case, plus 5, to kind of have all of the pieces that you're modifying highlighted here. So imagine I highlight the fact that I'm multiplying by 2 and then adding by 5. And or you can just work off what you had before, in which case if you were to add 5 to this, you could say this is also equal to 4x plus 6 plus 5. So that's kind of modifying the outputs, and you kind of keep track that, hey, this is my initial output, so output, and I am then continuing to modify the output by multiplying by 2 or adding by 5. And that's pretty cool. However, there's another thing that we can modify, which has great benefits for function notation in terms of representation. And that would be, let's imagine I have the same function. Let's write f of x equals 2x plus 3. It's a nice example. And this would be, we say, modifying inputs. So again, your x was your input. But what if I want to change what I'm plugging in? Maybe for some reason I want to instead plug in the number that's 1 greater than each of the inputs currently. Well, that would be, for instance, if my input is currently x, then I want to plug in x plus 1 instead. Now, why do you want to do this? I don't know. There could be some benefit to it, but in any case, it's nice to know that it's nice to figure out that maybe this is something that we could do. So let me write this. It's always nice to play around to see what you could do. Even if you don't know why you would need to do it, it's always fun to play around. Well, in this case, we could write your function evaluated at 1 more than what your initial input was. Now, how do you interpret this? Well, remember, what you put inside the parentheses is your input, and you place it wherever the x was in the initial equation. So you should have here 2 times, x plus 1. In this case, plus 3 still as well. And so now you can have f of x plus 1 equals 2x plus 2 plus 3. And so you have f of x plus 1 equals 2x plus 5. Isn't that fun? We can modify the inputs. And we can keep track of the fact that, hey, this guy, 2x plus 5, is kind of like f of x, but you just add 1 to the input. You can kind of store that this is what you're dealing with. And then if you don't like this notation, you could also say, like, maybe we call this guy g of x, and we say this other function is equal to our initial function, but with 1 more added to its inputs. And then you could say that g of x equals 2x plus 5. So you can name another function and say, hey, this function that I just made, g of x is 2x plus 5, that is essentially f of x, which is up here, which is 2x plus 3, only you add 1 more to each of the inputs. And I think that's pretty cool. It's a nice way to keep track of what you're doing, and it allows us to do a lot of cool things. And yeah, I think that'll be a good place for us to stop on this video. On the other notes, you could plug in whatever you want. If you want to change what the input variable looks like as well, you could do like f of smiley face is equal to 2 times smiley face plus 5, because you just plug that in, which should equal 2 times your smiley face plus 5. Maybe I put a circle around it so it's actually easier to read off there. But 2 times your smiley face plus 5. You can let an input variable be whatever you want, however you choose to represent it. Don't get too confused and lost on this idea. It's not a very crazy one that I'm using a smiley face here. Maybe I'll change the color of the smiley face as well to make it easier to see. Let's go like that. Cool. Style, maybe make it blue. You can like plug in whatever you want, and you can do the math with it however you would like. And well, yeah.